Today, I'll talk about Ford circles. I'll tell what Ford circles are. That's going to be the title of the talk, at least. And yeah, it will be very different in spirit from what we had last week, which was talking about the whole universe, or the evolution of the whole universe. There is a part 2 to that, by the way, just for information. It will be continued next week. Okay, so what are Ford circles? So before we go to Ford circles, let's think of a straight line. So a straight, so we're talking about straight line. Just give a feel for what I'm talking about. If I want to describe or characterize a straight line uniquely, unambiguously, you would say, and let's stick to straight lines on a plane. Like this is everything here today will be on a plane. I need to specify that because in general, a straight line can come out of the board also. Okay, but that's not what we're talking about. We're talking about lines on a plane. That means on this blackboard. Let's say an example of a straight line is this, right? That's a straight line, and by line we also mean that it goes all the way to the right and all the way to the left. That's understood. But we want to characterize this. That means to say that if I want to pass on this information to someone else, that this is, I'm talking about this particular line and not something that is tilted a little more. Right? So I want to specify exactly this straight line. Then we want to define certain things, right? So first of all, we build a coordinate system in our head. So let's say this is my coordinate system. Like I have two lines. That's this could represent X and this could represent Y, but I need some coordinate system, and this is my origin. That's how you go out. You can think of it as this is east, that's north, this will be south, and this is west. And if you want to specify where exactly you are in a car, then you need to specify exactly how far you're from the origin. Now, if I want to characterize this straight line, the first thing I will need is how much tilted this is, right? And that is usually described by an angle. You call it the slope. And let's say this is described by the angle theta. Give me the angle theta, that means to say how much is this tilted. And even after I specify the tilt, there can be many straight lines with the same tilt. And then you say that, oh, how do I fix that? I can tell the distance from the origin. Either I can give this distance or this distance or a perpendicular distance. Let's stick to this distance. So that's your C, right? So second will be distance from the origin. So distance from the origin, and let's say that's C. So that's a broad understanding we have about a straight line on a plane. You need a angle or the tilt and the distance. Now let's come to circles. So this was just a sort of a warm-up of what kind of a discussion we are having. And we want to now talk about circles, or just a circle on a plane again. And a circle again. So if you think of it, how do you characterize a circle? If you want to tell a friend, I have a, let's say, bangle if you want to describe your bangle to a friend, then you will say, oh, how wide it is, right? And the technical name for that is radius. So you want to say this is your circle, and circle is described by the radius r. That means from the center to the to any point on the circle. And again, now you want to have many circles, right? So the first characterization of a circle is radius. That means to say how like the center to that point if you want. And again, you can have this could be anywhere, right? It doesn't really have to intersect, it could be anywhere. And you want to also specify with respect to the origin, where is the center? And as I move the center, which is described by the position of the center, I can have different circles. So distance from origin. So that's our characterization, right? That's a straight line, that's a circle. But now I am going to talk about fourth circles. They're very special. They're a class of circles, but not really every circle does not become a fourth circle. So what is a fourth circle? So let me define that. So let's go to the other fourth. So, okay. Oh, by the way, any questions at this stage? That should be.
Well, rather a curious comment here.
Yeah.
Like, so what's the object of interest? The straight line or a circle or whatever geometric shape you're wanting to describe? But then the choice of the coordinate system becomes important.
Does it? Maybe I should say that the coordinate system was not important. It was the origin, right? So I'm standing here, like I didn't really use this X. Maybe, yeah, I mean, as a reference line, right? Yeah, angle with respect to a line. Like if I want to make this more precise, I would say that I don't really need X and Y. I need a straight line here. So it's like north. I mean, if you want to talk about where you are, first you specify your north star, and then you say, oh, how far am I, or at what angle I am from the north star. So first I need a reference, and this line acts like a reference. I don't really need the y-axis, correct? So like think of geometrically instead of the coordinate geometry. I'm just telling that it is not necessary to use the coordinate. But if you really want, then yeah, I mean, in terms of coordinates, this is y is equal to mx plus c. That's your equation describing that. And similarly, x squared plus y squared is equal to r squared. But I don't want to go there. I'm just wanting to think of it as a concept as to if I have a straight line, it is described by, or different straight lines can be specified by pick a line. This is a reference line now, not necessarily the x-axis. Could be the north star, direction of the north star, and this is making an angle with respect to that, and how far you're with respect to that line, and I pick a point on that line, so that specifies by origin. The same thing here. Does that help? And here I don't even need x and y. I just need this origin. Right? That could be a description needed. Does that clarify? That's a good point. I mean, I think at some very like we take this for granted when we are in a classroom, right? Oh, we always have a coordinate system and so on.
Mm-hmm.
Does that clarify your question?
Yeah, I mean, reference point, reference line, like, yeah, they are important.
Yeah. So the basic idea is to unambiguously specify a circle. Like that's what we do. Coordinate geometry, right? In the subject of coordinate geometry and mathematics, the goal is to specify a curve very unambiguously. Just writing an equation down should make it very clear that this is what we mean in a sense. Yeah. Helps. Okay, so I proceed. Okay, so now I want to, so out of all circles possible, I want to talk about fourth circles. And this is, I'll tell what the importance or the motivation of that. But as a geometry, it is just a description if you want. So first is, these are all circles which should touch this line. So I first draw a straight line. This is just a line. And one condition I put is that every fourth circle has to touch this line. And just for making this concrete, we can say this is x-axis, right? So that's just to make this concrete like we did earlier. And so think of any circle. So let me say I start with this circle, right? So just for purposes that will be clear, that's the first circle I draw, and it has a radius r. Let's say a pretty good circle, but let's survive. Any questions? There will be.
No.
Okay, so that's one circle of not radius r. Let's say radius r by 2. Think of r as unit. I mean, r doesn't really play an important role here. Let me have exactly same circle, 2 of them now. So, and let's see, keep this like this. So that's your second circle. And it's exactly the same radius r by 2. In such a way that this becomes the total. So let me bring this down here. So let's say this is 0, and that's your 1. By 1 I mean r, right? So this is 1 times r. So let's say this is r. If this is r by 2, that's r by 2, that's r by 2. So that's r. So basically the point is that there are 2 circles. So if I were to zoom out, so these are 2 circles, right? So let's see 2 circles. Right, that's how it is. Right. And now the point is, I said I'm going to define 4 circles. So 4 circles are any circle that touches this line, and it also has to be tangent to 2 circles. So now I have drawn 2 circles. I have to find a third circle, which is touching the 2 circles at 1 point each and the line. So I have to fit in a circle like this here. Okay. And it turns out that there is a unique circle that you can fit in. You cannot fit in any arbitrary circle. If you are given this radius, that radius, you can actually have a unique circle fitting in this region. Again, it has to touch the circle 1 point. Touch that circle. If you say it's tangential, so the technical word is it's tangential to this circle, that circle, and the straight line. And then the question comes out, oh, if that is the case, what is the radius of the new circle? Right? That's a reasonable question you can ask. That could be a curious question you could ask. Oh, if the bigger circle radius is known, it is known to be radius over 2, then what is the radius of the new circle? And it has a very, I mean, you can prove this, what exactly is the radius, but that's not what I'm going to do here. I'm just going to describe a very simple prescription here to get that, how you find that circle, not as a proof, just as an information, right? So here is how you can go about this. So let me say this is 0 and that's 1. By 1, I mean 1 times r, right? Whenever I say 1, that means 1 times r. 1 times this radius. So this is 0, that's 1. And
or you can just choose the radius to be half, doesn't matter.
all right, I choose r equal to 1. Yeah, that's a good way. That's better. So let's say r is equal to 1 temporarily, just so that I can work with numbers and not worry about letters. Just to avoid the clutter, that's all. There's nothing sophisticated in there, nothing deep in there. So that's 0 and that's 1. So if you're thinking of a number line, so this is 0, 1, there is 2 somewhere here, and so on. So all the numbers between 0 and 1 fit in that, right? That's ideal. Since this is r by 2 and that's r by 2, it is very clear that the center of the circle has to be on that half line. So this has to be half, right? So that's half. I'm going to write that half as 1 by 2. Since this came out as a fraction, let me go ahead and write the 0 and 1 also as a fraction. So I'll write this 1 as 1 over 1 and 0 as 0 over 1. 0 over 1 is 0. So I can always write 0 as 0 over 1 and 1 over 1 is 1. So I just wrote that as a fraction. Okay. So I have 1 by 2 then the question is, what is the radius of the circle? So the radius of the circle will be, remember the original was r over 2. Take the denominator of this fraction, this is 2, so it will be 2 squared. So that's r over 8, right? So there's a 2 and a 2 squared, so that's r over 8. That's it. Prescriptive. So next you would say, okay, so that's interesting. Okay, if that is true, what about now I have two circles here, so there's a circle here and another circle. There's a straight line. Again, can you fit in a circle between this? It
Why
turns
is
out
that true? Like, I mean, you can find it out, or like, I mean,
you can find it out. I will give I'll motivate that in the next part. But for now, let's take it as a known result, because that will take me into an algebra and it is not really instructive. It doesn't help much. It's
okay,
instead
fine.
to say that.
So the point
This-
is you can always find it by
Yes.
dividing
All
by,
that
okay. Mhm.
correct. And I will give it now. Let me proceed, and it will come out nice, right? Okay. So what I did here now is, okay, I got this to be half, and how did I get this half? I just argued that this has to be at the center, but there is a better way of looking at this. Add the two numerators, 0 and 1, that's 1. Add the two denominators, 1 plus 1, that's 2. So that turns out to be an interesting way of getting that. And then you ask, okay, what about the next circle? I can fit in a circle here also. So you can fit in a circle in here. And then you again ask, what's the radius of that circle? Okay. So first of all, I need to have a position of this. So where is the circle touching? I need to have this position, right? So this position will be, so here is a prescription. This is touching the circle at half, and this is touching the circle at 1 over 1. Add 1 plus 1, that's 2. Add the denominators, 2 plus 1, that's 3. Notice this is not normal addition, right? This is not addition of two fractions. This is a mistake in addition if you want. This is 1 plus 1, and you add the numerators separately and denominators separately. That's not normal addition at all. That's not how numbers or fractions add. But if you do this sort of addition, you get 2 over 3, and that is exactly the position of the circle. Absolutely, and it turns out to be exact. And then what's the radius of the circle? You say it is r, again r over 2. You begin with r over 2. Get rid of the numerator, only the denominator, so that's 3 squared. That's r over 9 into 2, 18. It's significantly small. Okay. Questions? I can do this on this side also if I want a circle here. So do 0 plus 1, that's 1. 1 plus 2, that's 3. Radius of this will be, again, it is 3. I don't care for the numerator when I'm calculating the radius. It's r over 2 times 3 squared. So that's 18, r over 18. I can keep doing this. So the next one will be somewhere here. So this will be 2 plus 1, 3. And 3 plus 1, 4. Hit another one here. That's 0 plus 1, 3 plus 1, that's 1 over 4. I can do that here. So that's 1 plus 1, 2, 2 over 5. Hit another one here. So that's these two, right? So that's 3 over 5. And so on. Okay. So what I'm doing is that it has to be touching the horizontal line. And I can pick any two circles here. And if they are tangential, if those two circles are tangential, I can fit in a third one. And I have this very, at least there's a pattern you find in finding the radius, and that is that first find the position of the circle, which is got by a fraction, and the radius is determined by the denominator part and the square of that. So in fact, if you say, I mean, so now when you're talking about a fraction, so what we have written now is m over n. So any number that can be written as a fraction, right? 1 over 4, 3 over 4, even 7 over 5, they are all fractions. But now since I'm restricting my circles to be between 0 and 1, let me say that m has to be less than n. So notice that, so they're all less than 1, right? 1 by 4. So that number on the numerator is always less than the number on the denominator. And this represents the numerator, and that's the denominator. So that's two numbers. And the position of this circles is this number. Remember, r was equal to 1. I can put that r if you want. So r is 1, so I don't have to do that. So remember, I need to describe the circles. 1 is the position that describes the position. Right? Where is the circle? So if I specify where on this line is the circle, that's the position. Right? So that's the position. And I have to also say, what's its radius, right? A circle is described by its radius, and I said that that's described by the denominator of this number. So this is r over, that was a 2, and then only talk about the denominator, that's n squared. It's the same idea as I was doing it, it's just that I have captured that in the form of an equation. For every natural number m and n, like by like countable numbers 1, 2, 3, 4, 5 m, and so by here m and n are 1, 2, 3, 4, and so on. Right. So give any two possible numbers m and n, and this describes a description of what I have drawn in here. Right? This is an interesting geometry in the sense that it can go deeper and deeper. It doesn't stop here, right? I can keep doing this forever, and it captures an infinite set of circles. And the most interesting part here is that there is a circle corresponding to every rational number on this line. By a rational number is a number that can be written in this form, m over n. For every rational number, there is a circle you can find, and that circle radius will be this. So rational numbers has interesting properties. So I'll tell a few things about it in a few minutes. And here we are saying that there's a one-to-one relation between rational numbers and four circles. So what I'm saying here is that, so this is kind of a interesting result here. So here, this is the rational numbers. So rational numbers, it is m over n. Right? For every combination of two numbers, there is a fourth circle. So the connection between the two, and the four circles have a position described by m over n, times r, and its radius is r over 2 and square. Right, that's what I mean. Like there is a property, there is a set of numbers called rational numbers, which is any number that can be written in that, any number that is a fraction, put it like that, with the numerator being less than the denominator. You can associate a circle for it, a very unique circle to that, whose position is, it's one of these circles described here, and that's the radius of the circle. And if you want to, so what that means is that if I want to study rational numbers or the properties of some property of a rational number, I can visualize it on, maybe I can visualize it on a fourth circle, and the opposite. If I have a result in rational circles, I can get a analogous result in 4 circles. And what I will do today here is that, okay, so these are circles, each circle has an area. You can say, what if I add the area of every possible circle that can be represented on this line? And it turns out that that's a nice answer in there. Yes, Christian, please.
Yes, sorry. Just that. So that seems to be the position, and that's the radius of the circle.
Correct.
Yeah. But these both do not seem to be independent in this case, right? Somewhere we will be able to relate the radius. We'll be able to get the radius from the different positions of the 4 circles. I mean, here in a case of a normal circle, they are independent, definitely. The position and the radius. Position from the origin and the radius.
Yes,
but in this case,
yeah, they're related. So what you're asking, if I understand this correct, is that I can, if I have a straight line and let's say I have some arbitrary number m over n, I can fit in many circles, right? So this, I can fit in this circle, I can fit in this circle. There are many circles I can have which is positioned at that point. But here I'm specifying that the moment I give the position, there is a very special circle, only that particular circle which has a radius of r over n2n square. Only that's allowed. That's the circle I mean I have in mind. That's what a 4th circle.
Yeah, yeah.
Does that
So they are not,
that,
yeah, so they are not independent, right?
the position and radius are not independent, yes.
Okay.
The moment you give the position, radius is fixed.
Fixed. Okay.
Yeah, the moment I pick the position, the radius is fixed. So if I'm here, there's a big circle. If I'm here, that's a slightly smaller. But if I'm in between, it doesn't mean that it will be the average of the two. It is even smaller, right?
Yeah.
So in a sense,
This is not like a coordinates in case of the circle, normal circle.
No, I don't think so.
Yeah.
So Shajesh, like, I mean, this is quite interesting, actually. You suddenly told me something here that all the rational numbers are represented, which means that the whole of 4th circle, like the whole of a rational number algebra will also be represented by a unique 4th circle, right?
Exactly. That is the nice part. That is the interesting part of 4th circles. Like this is a very deep result there, because if you want to study rational, or if you know a result in rational numbers, you can do the opposite. Usually it's the opposite. It is easy to visualize circles and get results in circles, but it's not very easy to get results in number theory. When you're working with numbers, it is harder. So you use the knowledge of circles to get results in this. At least that could be one of the ways to say that. It could be the opposite also. So yes, yeah, that's the nice part of it. I think that's why it's important. But there could be more reasons why it's important. Yeah. Any other comments or questions?
I think we
Okay,
can.
so yeah, so what I will address here is that what the area of this, these are infinite circles. You would say, okay, what's the total area of that? That's what we can do. And maybe since the question came, I mean, I'm just deciding what exactly to do. Okay, so maybe since rational numbers came in, so maybe I should just motivate a little bit about numbers, just as to let's see. So let's so the first set of numbers we can think of, these are called the natural numbers, right? So these are natural numbers, and that's what by that what we mean is 1, 2, 3, and so on. Right. And immediately when we have a set of numbers, we can ask, oh, so few properties of numbers is this countable or not? These are the questions we ask. Is this countable? And what do we mean by countable? Exactly what we mean. 1, 2, 3, 4. Can I count? Okay. It could be infinite, but it should be countable. I should be able to keep going. And as far as there is an algorithm or a procedure to count, that's good enough. And the only way we know how to count is using 1, 2, 3, 4. That's what we mean by counting. That's what I mean by countable, right? Then we can ask, is it finite set of numbers or is it infinite? And once most of the numbers we will talk about here will be infinite, but the moment you have infinite, we will ask the question, is it countable infinity or not? And I'll come to that in a moment. The next one will be, is it ordered or not? By ordered, I mean, if I have a set of numbers, is it possible to talk about, give me two numbers, is this on the right or left side of the number, or is it greater than or less than the number? So these are the properties of numbers we will talk about. Next, we will talk about by dense, I mean, if I have one number right next to that number, how close to that number can I get? Like, for example, 3.1 is very close to that. But between 3 and 3.1, I can find another number, right? 3.15. Between 3 and 3.15, can I find another number? And I can keep doing this. If I can keep doing this forever, then you call it dense. If you cannot do this forever, then you say it is not dense. For example, this set of numbers is not dense, right? Because between 2 and 3, there is 2.5, but there is no such number here, right? In this set of numbers, that's not there. So these are some of the properties you can think of. So that's natural numbers. Next is whole numbers. It's just 0, 1. You add a 0 to that. So that's called that's just a name associated with that. And this has almost all the properties of this. And then you say that, oh, how do you count this number? What's the like or a basic question you can ask is, which set of numbers of the two I have listed, which one has more number of numbers? That's a very odd sentence. Which set has more numbers? And naively, you would think that, oh, there is a extra zero here, so this should have more numbers, but that's not the way to look at it. We have to count, right? So if you notice, this is just a label here. I can associate 1 with 0. So I will say 0 is 1, 1 is 2. So this is, I'm connecting the two. This is what I mean by counting, right? I'm counting 1, 2, 3, 4. And I can keep doing this for every number. I can associate this, and in that sense, that's what I mean by in that sense, this to have the same number of numbers. Like they have, both are infinite, but they're countable infinity, and they have the same number of numbers. If that makes sense. Any questions on that? That should be. You're not familiar with that concept, that should be
equal set, right? Like equal.
Yeah, it's an equal set. Yeah, these are just labels. I mean, these are just labels for these numbers. Change this to 1, 2, 3, and they're the same numbers. So that's whole numbers. Then you can say integers. Integers is right, so this means there is 0, plus 1, plus 2, and so on. And this is minus 1. This is minus 2, and so on. And you would now say that, oh, I'm going in two directions, that this should surely be more than this. But again, remember, if you can count them, if you can find a procedure to count, that's good enough. So you would say that this is my first number, that's my second number, that's my third number, that's my fourth number, that's my fifth number. So I have a procedure to count, right? That's my sixth number, that's my seventh number, and so on. I can do this forever, and that is a very clear procedure to count. And that means the number of or these two are equal sets, right? I think that's the language you gave me. That's easier to say rather than the same number. Of
Yeah, I mean, basically it is one-to-one mapping. That's
Correct.
what you're having.
Yes, so technically you would say that's a one-to-one mapping you're doing on this. So that's integers. So then you would say, okay, so that's good enough. Now you come to fractions, right? So then you say, okay, so this is called rational numbers, or let me just say fractions, right? So this is more correct word is rational numbers. And this is any number in between. So for example, 3 over, so 0, like there is 1 by, so this have a number line and any number that can be written as a fraction, for example, 5 over 6. And you would say this is m over n, like that's what we were talking about earlier. So any number that can be written as a fraction, it doesn't have to be less than 1. So this can be 7 over 5. That's also a fraction. You often think of this as, oh, what about 14 over 10? There is 14 over 10 and there is 7 over 5. So there is one understanding here that write this in the simplest form, because these two are the same numbers, right? So you don't want that ambiguity. You want a one-to-one mapping, and so that's a way of doing it. And then you again ask the same
But you will also consider like all these like 1, 2, 3 also as like fractions, because they can
Yes,
be like
1,
2
2,
over
3,
1, 3 over 1, right?
exactly. So 1, 2, 3 can be written as, so 2 can be written as 2 over 1, 5 can be written as 5 over 1. So every number, every fraction that you can think of belongs to rational numbers. And then you again ask, okay, now that's a lots of numbers. You can just visualize it, that when you visualize it, then you say that, oh, this is 0, this is 0, 1, 2, and now every number, like think of a very point, visually speaking, almost infinitely close to 0, and you can write that as 0.000, write a billion zeros there and then a 1. That's a very small number, but that can be written as 1 into 10 raised to 11 or something. Right? So that's 100 billion. So that's very close. That's, so visually speaking, you would think that, oh, this surely has more numbers than that. But remember, my procedure to, or my prescription to say that there are infinite numbers is that I should be able to count it. And then you say, how do I count these numbers? Rational numbers, every number, how do you count that? A simple procedure could be, it's m over n, right? So you need 2 numbers. Any combination of 2 numbers is a rational number, and you just want a trick to count it. So you would say that, okay, and it could be positive or negative. So a trick could be, so these are all natural numbers. So this is 0, 1, 2, 3, and so on. And this is one way, one very rudimentary way if you want. That's 2, 3, and so on. So for every point on this plane describes a rational number. I pick a number on this line, that's 2. Pick a number here, that's 2 by 3. So this represents 2 by 3. This represents 3 by 1. So every, so I keep going here. Every number on this plane in this form of writing represents so that's a way of collecting or labeling all my rational numbers, and then I have to find a way of counting it, right? So remember, if I can count, that means it's exactly the same. So I can count. So I start from here. So I go here and go this way and go here, count. I can keep counting, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I can keep doing this. And I will never, so it's a very unique way of counting that wherever you are, you will come on. And then you say, oh, what about that? So every time you go here, then you can go here. So there's a way of counting this out. It's just that, so for example, what I have to do is that once I reach here, then I will do this also, and then go here, then do this, then do this. But exactly like we did here, right? 1, 2, 3, 4. And there is a unique way of counting. So in that sense, what I've shown is what this means is that in this way of saying that if it is countable or not, the number of elements in the rational number set is exactly the same as the number of elements in the natural number set, which is very non-trivial if you think of it as the visual way of representing how many numbers are there. But that's a statement that it's the same number of elements in both rational numbers and natural numbers, which in the beginning comes out very non-trivial. And we are working with this set of numbers. It turns out that then you ask the question, for example, let's say if you have a straight line, right? So these are two, pick any two numbers here, and you have a rational number, and then you ask, is there any other number in between? Like, or what I'm saying is that if you have a number m over n, does this collect all the numbers, or am I missing something? And it turns out that, yeah, you miss a lots of numbers, which if you restrict yourself to this, for example, pi is a classic example, right? Pi is 3.14 something, but it cannot be written in this form. Pi cannot be written as a fraction. Square root of 2 cannot be written as a fraction. So it turns out that there are an infinite number of numbers that cannot be written in this form, and those are called irrational numbers, right? So that anything that cannot be written in this form, that would be called an irrational number. And now that leads us to the question that I said rational numbers are countable. Are irrational numbers countable or not? And you say that that's not countable. And here is a very simple proof of this. This goes back to Cantor, I think. So irrational number, remember, cannot be written as a fraction, which means that I will never be able to end the number. If I write it as a decimal, it will keep going. It will keep going forever, and it will never repeat. It will keep going forever, and it will never repeat. So let's say this is 1.2357, and it keeps going. So that's one irrational number, and that's 3.152. Second number, let's say that you collect all the irrational numbers in an Excel file. Right? That's what it means to say that it's countable. That means to remember an Excel file as is 1, 2, 3 on the left, right? So if I can fit in all the irrational numbers on an Excel file, that means it's countable. And let's assume that it is actually countable. I'm going to prove that it is not countable, but let's say that it is countable. So I have put in all the irrational numbers in a row, right? Not necessarily ordered, just you went and collected all of them from a form and put them in an Excel file. And then you do the following. Pick this first number in the Excel sheet. The first digit of that is 1. Remove that 1 and write something else other than 1. Let's have the prescription that I will start with 1 and make it 2. So I started with the first digit of the first number and made that 2. The second one, I said this is 3.1, and this doesn't have to be started with, this could be 33 also, right? It doesn't have to be the same one. Now, this was the first digit. This is now decimal after that. The first digit after the decimal is 1. Again, increase it. So that's increase it by 1, that's 2. The next number could be 5.732. So this was 1, 2. The third digit here, I'll say is 4. And I keep doing this. So every next number in the next in the list in the next one, I increment by 2 and I keep writing that number. And then the point is, so now I have created a new number. How did I create the new number? Went by this prescription that 1 became a 2, 1 became a 2, 3 became a 4, next one, and so on. This number is not this because the first digit doesn't match. this number is not this because the second digit after the second in this or the first digit after the decimal doesn't match. This is not this number because it doesn't match this. And I can keep doing this and I can claim that this number doesn't belong to this list. But then that's a number, right? So we have shown that there is a number which I can write, which does not belong to this list. In that sense, the real number set is not countable. So this is called the Cantor's proof. If I did not say that plainly, I will recommend that you look this up. It's a very straightforward, very powerful proof, which is almost one in a sentence you can finish it, but a very powerful proof how you can show that irrational numbers are not countable. But anyway, so just for completeness, let me do one more thing. So this is irrational numbers. You can keep going here. So this is real numbers. I won't talk about this. Let me not, so that we can finish whatever I aim to do. So that's real numbers. You can keep going here. So this is complex number. Next comes complex numbers. Then there are quaternions. And then there are octonions. And then that's it. That's the end. Okay. In fact, apparently, there's a proof that you cannot build anything beyond that. So that's a maximum you can go. And of course, you will ask, well, what is the
Shajesh, that could be just, that could be the, what do you call? That could be the limitation posed by, because we are thinking in terms of 3 dimensions only. Like, so I can think of it as a graph, right? Quaternions are probably I mean, you can create it like 4 quadrants and the numbers that relate.
No, it turns out that actually the history of quaternions is interesting, because the moment complex number came up, remember that it can be represented in 2 dimensions. Immediately the point was, well, let's me do this in 3 dimensions. And it turns out that you cannot do that. I mean, that's what Hamilton struggled for a long time. And then he realized that he has to go into the 4th dimension, so-called 4th dimension. Like there are 3 complex numbers you have to build in to do that. So, or you can think of it as polymatrices, does the same job. So it's not in 3 dimensions at all. Like, or even that visualization that you are suggesting, it doesn't work here. So this is 4 and this is an 8. These are 8, if you want, dimensions, not really dimensions, but even better, claim is that you cannot go beyond. So that's just for information. I think we can have a complete discussion on this another time in some other place, I think. But
okay, yeah.
Oh, talking about dimensions, what is the dimension of this 4th circle?
If I'm not wrong, I think it's not known. I mean, you mean the fractal dimension, right? We are not talking about the dimension of, like,
Yeah. Yes.
The fractal dimension. If I'm not wrong, it's not known. They haven't calculated. Like, it has not been done yet. It's an open problem, I think.
You can't use the same prescription you used in the first lecture to find it. Yeah,
you cannot. I mean, yeah.
Oh.
I mean, it's only very special cases you can actually find that it's doable. I think, again, correct me if I'm wrong. I mean, look it up on your own also. To my knowledge, it's not, because this is a class of Apollonian circles and or gasket. It's not known, I think. I think numerically, I think they might have made some developments there, but in general, you cannot prove it. Yeah. Does that help? Yeah. Okay, so it's 5:24.
So Shajesh, quickly relate how 4th circle is a fractal. Quickly relate it in a minute. Like you in the very first lecture showed a set of fractals, right?
Yeah. So yeah, I particularly very consciously did not want to use the word fractal. Venkat brought it up. Because, I mean, okay. I personally think that a fractal should be self-similar. I'm not sure how strict that definition is. I would think that that has to be self-similar, but maybe not. I mean, sometimes maybe you can just say that if you can have this infinite structure, that is sufficient to be for it to be a fractal. But if I require it to be self-similar, by self-similar, I mean that this big thing should be there inside. Like it's like saying that you are there inside yourself, like a very non-trivial concept that you are part of yourself, like the whole world is inside you, kind of, right? So you're saying that can one small piece, for example, this piece here, right? So here, can this have the properties of the whole thing? So is this self-similar or not? And I'm not sure if it is self-similar or not. And again, is that done or not? I don't know. So that's why I did not want to use the word fractal. But yes, it is a fractal in the sense that, yeah, there is an infinite structure in there. In that simple sense, it is a fractal. And you can associate a dimension to that. So in that sense also, I think it will have a fractal dimension associated with it, how much space it fills in. So in many ways, in that sense, it is a fractal, but then I associate
Probably not,
self-similarity.
because what about snowflakes?
Snowflakes are fractals. In fact, it has this interesting feature that its perimeter is infinite, circumference is infinite, but its area is finite. So that's a very non-trivial thing that
No,
you
but
think of a finite object.
just going by your self-similar definition.
Yeah, it is self-similar. Yeah, you can. Yeah, it is self-similar, right? I mean, you can think of
Show
like
it.
how you. Yeah. So, for example, you take a triangle. If you can see that. So start with a triangle. Right? This is how you will build a snowflake, right? So
Yeah, but then you
split this.
take the third off on sides, but that is not going in inside yourself, right? Is it?
You are, in the sense that now let me finish this. So this is how you will build a snowflake, right? So that's what, and then you start splitting this more.
Yeah, I get it. But the point is, like, does it mean to say that you're going inside yourself here? You're just
Yeah,
repeating a pattern here.
Yeah,
And in that
whatever.
sense,
For example, this piece is there inside here. If I take this and blow it up, I'll get this.
but that way the four circles will also be.
I have this feeling that, see, the radius of the two circles are not the same. So, for example, this, maybe it is, I don't know. Let me not say anything. I don't know.
I think
Like-
fractals are better defined if you say that the description does not change if you keep changing the scales. The description
Yeah, but
requires.
yeah, and I claim that even though here there is apparently only single scale R, at this scale here, there is a R1 and an R2. There are two radiuses, right? If I want to describe this piece here, there are two radiuses. So that's a two parameter problem
No,
in a deeper
I mean, I
scale,
forget.
but it's a one parameter problem at a very global scale.
If I forget that R by 2 exists also, just with, oh,
It is not Venkat. It is exactly what Shajesh is saying.
yeah,
that-
okay, I understand.
Yeah,
understand the
like
problem.
whatever is R by 2 representing, that is not repeated at the bottom. Like, I mean, that
Yeah.
when you change the scale, it is not the same thing.
Well, I cannot get R by 2 using only the small circles you're saying.
Think about it. I don't know. I
Yes,
don't want to make a
yes.
strong statement. Yeah.
Sure.
So I don't know. That's the better way of saying it. And I mean, I have tried to see if I know that it is self-similar, then I can do a lot of things in for 4 circles. But I have not been able to construct one piece out of the other. So that's my inability. It doesn't mean that it cannot be done. I have not been able to do this. Yeah. So that's the way to say. Yeah.
Okay.
Okay. Shall I proceed? Christian?
Yes.
Yes, too. Can I proceed here? Okay, what I was doing. Yeah, so yeah, so this was a digression. I didn't mean to go here, but I think okay. So that's 4 circles. Yeah, let me not 4 circles are part of a Polonian gasket, but keeping time in mind, let me try to finish this in the next 10 minutes or so. So it's good to talk about area of 4 circles, right? So we are talking about, I have said that give me any combination of the position of circle, right? And the radius of circle. So this is now equation. So let me describe this better. Right. So this is again, this is your 2 circles. That's 1, that's 0, and I keep drawing this, right? And you keep, it has to be touching the bottom line. So that makes, so you collect all of the circles, and now I want to add them, add the area of this, right? So area of this piece, area of this piece, and as you will see that as they get smaller and smaller, the area becomes tiny, but there are infinite of them, so it's not very obvious. Even if they are small areas, if there are infinite of small tiny elements, it can actually give you either an infinity, sometimes an infinity, sometimes they can balance and give you some finite quantity. So the area of this would be, so area is equal to, so there is this circle which is at 0 point, that's kind of special. I want to keep that separate. And that's has an r/2, right? That was the radius. So keep that separated. Remember, the area of a circle is pi r squared, so it's r/2 squared. Rest of them, when I'm talking about the area, it is only the radius that is important. The position doesn't matter. Right? Whether these 2 circles are identical, whether it is this or this, it doesn't matter. But there are 2 of them. That's the point. So there are 2 circles of half radius, but one of them I'm keeping it separate, so that's one of them. There is 1 circle of r/8, 2 circles of this, and so on. I start collecting all of them, and I want to have a prescription to that. So the plain way of doing this is, so you have to add all possible m over n, right? So for every m over n, there is a circle. So this is adding. So this is so for every n going from.
What did you say about the first set? Like there are 2 of them or just one?
First one, I just separated this out because
Oh,
it
half
doesn't
and
fall.
half actually. Okay. So half of
Yes,
this and half of that. Okay, correct.
half of the set, half of that. So this is the first one, right? So this is n. Okay, and then I have to also sum over m. So for every combination of m and n, right? But then m has to be less than n. So m starts from 1, and then it doesn't go beyond n. Right? That makes sure that this is always less than 1, right? But even that is not sufficient. Remember, if I get 2 numbers like 1 over 4.
Or probably
and
n-1, right? Shouldn't it be n-1?
I'll get rid of that in a minute. Yeah.
Okay.
Okay, so that's 1 over 4 and 2 over 8 are the same ones, right? So I don't want, so that's kind of that kind of combinations. And you also have many things that do not belong to this class, and that is got by. So you will, for every m and n, you look for a if and not condition, like is so you put a test, right? You say GCD, this means greatest common divisor of n and m. If this is equal to 1, this is okay, good. if this has to be equal to 1, and then if it is, then you said you have to add them up, right? So then it is pi r over 2n squared. So that's a circle, but then there are how many circles is decided by, for every m to n, you have to ask, oh, if this is actually belonging to the simplest structure, right? You have to get rid of all this 2 over 8 or 4 over 16, all this has to be striked out. And they have this feature that between 2 and 8, there is a common divisor, right? 2 and 8 has 2 as a common divisor, 4 and 16 has 4 as the common divisor. If there is any common divisor, then you get rid of them. So if the common divisor is 1, then you keep it. That's a condition you put in. So what I mean by that is, let me tell, like I can make this more descriptive. So let's start with n equal to 1. And m can be only going from 1 to m, so that's only one possibility, right? Between 1 and 1, that's common divisor is okay. So then I'll define a function called phi. So phi of 1 is 1. There's only one circle with radius 1. That's what it means. Let's say n equal to 2. Now n can be equal to 1. Right? 1 and 2 has a common divisor as 1. And 2 and 2, the common divisor is.
Stop a minute. The first, like, so the point is the first option itself is the first term in your area. That's the radius r by 2 already there.
Correct. But then I have to ask how many of them are there.
No. The point is, like, you have already separated out that as the first term. Like, I mean, area equals pi r to r over 2 whole square. You have already taken care of that.
Oh, this one. No, this one is this piece here. And the first one I'm counting is this one. So this is a kind of an outlier. I mean, I don't know how to put it, so that's why I've separated this out. That doesn't come in.
I was thinking that you will only count between 0 and 1. So you are just considering half of this side and half of that side. But okay, go ahead. Yeah, now I get it.
Okay. So you would think that there is 2 also, but between 2 and 2, the common divisor, greatest common divisor is 2. So that doesn't belong here. So phi of 2 is again 1. Again, how many of them, right? There are 2 possibilities, or only one picks out. So, or you can say that this was 2, but then I strike it off because they have a common factor between them. Let me do this a few times and you'll see the pattern. So this is m. Like this is 1, 2, 3, right? That's the 3 possibilities. Between 1 and 3, it's okay. Between 2 and 3 is also okay because there is no common divisor. 3 and 3 there is, so I strike it up. Okay? So there are 2 of them. So phi of 3 is 2. N equal to 4. M can be 1, 2, 3, 4. 1 and 4 is okay. 2 and 4 is not possible because they have a common divisor. 3 and 4 is okay. 4 and 4 is not possible. So it's 4. Phi of 4 is again 2.
What is that phi?
The technical word for this, this is called Euler's totient function. It is.
How many circles are possible?
In this context, how many circles are possible for each n? Or if you have 2 numbers, how many of them are coprime? This is also called coprime. Or how many of them are such that the greatest common divisor is equal to 1? There are how many such combinations between them? And I'm just doing, let me take, let's say 5. N equal to 5 is a good thing because it's a prime number, right? So since it's a prime number, it won't have a common divisor between any numbers. So this will be m equal to 1, 2, 3, 4, except the phi itself. Right? Phi is not. So all of them will come. So phi of 5 is actually 4. In fact, for any prime number, pi of 11, for example, will be 10. Pi of 59 will be 58, right? And so on. So this is called Euler's quotient function that allows you to do the sum. That's what it does. So this whole thing is doable now. And now the area becomes bring out the pi r squared over 4 out. So that is 1 plus, there is a series still remaining. This is n equal to 1 to infinity. This I said is Euler's quotient function, right? That's phi of n. This is just a simple thing, how many circles there are, how many circles of radius n, and that is, if that is there, so it's n raised to 4. Okay, so that's a step. We are counting this area. And this is the non-trivial. Now, how much is that equal to? It turns out that that's a well-known series. In fact, it can be given in terms of Riemann zeta function. I cannot prove that. It's out of my ability. So I would say let's define. So this is Riemann zeta function, a very popular. There are most popular mathematics unsolved problem is connected with Riemann zeta function. Most popular, I mean the most. Many of them popular ones, right? So okay, so Riemann zeta function is zeta of s is n equal to 1 infinity 1 over n raised to s. Remember, this is like if, so this means that zeta of 2, for example, is just 1 over 1 square plus 1 over 2 square plus 1 over 3 square and so on. That's what we mean by that. And it has a very interesting structure. This is zeta of minus 1. We'll take it upstairs, right? So it is 1 plus 2 plus 3 plus 1. And that has this non-trivial result in there also. But this is a well-known function, and it turns out that this series can be written in terms of this. And this answer is pi r square over 4 is 1 plus zeta of 3 over zeta of 4. So that's the area of all this 4 circle. And this is a, well, I mean, this is a number. It's like a pi, right? Pi is a number that can be calculated to any digit you want to. Similarly, these numbers can be calculated known to any accuracy you want. So that's the area of the 4 circles, and that seems yeah, that's where I can stop. I went a little quick at the end, but hopefully helpful. Yeah. Any questions? I meant 10 minutes, 15 minutes cross.
So, so you are saying that area of 4 circles, the way you have described, is an irrational number?
Yes, there's a pi. Any area would be area of any circle will be irrational because it has a pi, right? Isn't that true?
That is, yeah, I never thought of it. That's nice to know. But I was just
But
going
you're,
by
you're probably asking, is this number irrational or not?
Yeah.
Right?
Yeah.
I think so. Pi of, I think all the zeta functions have pi square, pi 4 in it. So I think they're all irrational numbers. But I don't know. I mean, is Riemann zeta function an irrational number or not? I don't want to say wrong. Yeah, probably they are.
Do you know what zeta of 3 is, or like zeta of 4?
Zeta of 3 cannot be known, right? It's only the even numbers that have good are summable. The odd numbers cannot. They do not have a good representations, right? That's the way it is. Yeah. Like one of them has, like zeta of 4 is has a closed form, but not zeta of 3, I think. Something like that. It might be with the negative numbers. I'm not very sure. Yeah.
So another
Does that-
question, another question. So when you started out calculating the area, you said that, oh, there are infinite number of them. So the area should
Mhm.
be infinite.
No, I didn't say that. Just because you have infinite of something doesn't mean that it should add up to infinity. If they all go smaller and smaller, for example, a classic example is 1 plus 1 by 2 plus 1 by 4 plus so on, right? So these are infinite of them. But if I add them, this is not infinity, right? If this is equal to 1 plus over 1 plus 1 by 2, right? So just because it depends on how much they're, so one is the growth of adding and the other is that they're also decreasing. So in that sense, they don't add up. And then you can ask, oh, how small, at what rate should you be decreasing? Where is that borderline where you get an infinity or a finite thing? And that is, I think it is log of log. I think you can keep doing that. So I think you can ask that, but I don't think that barrier is can be determined clearly. Yeah. Did I answer?
Yeah.
Comment?
So there is another thing I want to ask, like, so you created this set of 4 circles by creating two circles. One of them is starting at origin, another one is at 1. You can also have another 4 circle at 2 or 3 or 4. That's a repeated
Sure.
pattern, right?
Sure. Yeah.
And like, does
Yeah.
that amount to anything and discussion? Because I know that Apollonian gasket, you cannot probably have this kind of feature because that is a circle. Those are the circles or tangent to a circle, not a straight line, right?
Yeah. So I think since you brought it up, like these are.
Or maybe that is the same thing because circumference can be mapped onto a straight line.
Yeah, like all this depends on what is called an Apollonian gasket, what Prachi pointed out. You can say that if you have one circle, right, and then let's say second circle, now that comes the third harder one. So that's your, okay, that's not a good circle, but still that's the third one. And now you can ask, so these are tangents, right? The 3 circles that you can are tangent to each other. And now you can ask that how many circles can you fit which are tangent to all 3? And one is easily visualizable, that's this. But then you will ask what is the radius of that. But then there is one more, it turns out, and that is this. So this is our, let's say R1, R2, and R3. So given R1, R2, and R3, the question is find R4, right? So give me the radius of this and this. So there are 2 solutions just by visualization, and this is what we call Descartes theorems. And again, I have not tried to prove it, but the theorem is that these radiuses satisfy 1 over R1. I think I need more space. So this is 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. That's what, so this is all known. This is unknown. Think of this as X squared is equal to 2 times 1 over R1 squared plus 1 over R2 squared plus 1 over R3 squared plus 1 over R4 squared. That's a quadratic equation in 1 over R4. Think of this as curvature, like think of Ci as 1 over Ri. This is basically an equation in curvatures. And this is a quadratic equation in 1 over R4. And the answer to this is, if you want 1 over R4 is equal to 1 over R1 plus 1 over R2 plus 1 over R3.
Oh, sorry,
Plus or
which is
minus.
R4?
R4 is the radius of this and this.
Ah.
The two circles, right?
I didn't understand. Oh, both how are both radius same? I didn't understand.
They're not the same. There are two solutions.
They're
Two
not
solutions.
same.
okay,
They
sir.
have two
Okay, okay.
solutions.
Oh, two solutions. Sorry.
Two solutions.
Yeah,
So that's so one of them is a small one and one is a larger one, and you get it out of this. So this is 1 over R1, R2 plus 1 over R2, R3 plus 1 over R3, R1. That's what Descartes found. Now we are talking about 4 circles. That means one of the circle has infinite radius, right? So if you want 4 circles, you say R3 tends to infinity. Right? That means that's very large. Then if you have a very large radius of Earth, it's practically flat. So it's a straight line. And then you get 1 over R4 is equal to 1 over R1 plus 1 over R2 plus or minus 2 times R1, R2, which is having a nice feature that this is square root of R1 plus or minus square root of R2 square. So for 4 circles, it's much simpler.
Question, like, but once you make R3 infinity, what will be the outer circle? Like, there is only one possibility.
Good point. Good point. So this was my visualization. So I think this is how it is. Okay, so what is the outer circle, right? So this is, so let's say this is one circle. And let's say this is my second circle. Hopefully it comes out. Oh. Right, that's your, this is surely one solution. Okay, that's a positive solution. The negative solution, I think, is this. You can keep going here and it will touch this at somewhere at this side.
I see.
This, you'll be able to touch that.
Interesting.
Yeah.
Maybe if you consider that, it will be a fractal.
Yeah, there are, I mean, that's correct. I mean, you can see that already, right? So you can, if you have a circle like this, you can fit in many circles, right? So you can do this. Yeah, I don't know. It's hard to see because this has to be tangent. to the
I
circle.
think, Venkat, you will eventually, if you go the outer circle, you will eventually reach the starting point of the talk, like that 4th circle. Like, so right now, Shajesh started with the these 2 circles which are not of the same radius, right?
Yeah.
But the beginning of the talk was with the 2 circles which had the same radius.
Yeah.
Right? But if you
Yeah.
continue going the outer circle, then probably you will reproduce that whole pattern again.
And I should say that there are not many known results in all this. Like in any of these things, you take a very few results and then you stop.
The problem is in 4 circles, we are restricting the space to one side, right? I feel that's the problem. We should not restrict the space to one side. I mean, in a Sierpinski triangle, like you did in the first lecture, it covers the entire space, entire 2-dimensional space.
That might be good. Yeah, that's what you do in Apollonian, and that might see Apollonian gasket has a, yeah, again, yeah, that, you might be right. But then it
So
doesn't
that
have
has
this feature that, of rational numbers. If you want to connect with rational numbers, you want this only on one side, right? I was
guess
more
that
interested in the rational number set.
okay.
That is very, very powerful in 4 circles, actually. I didn't realize that you have the whole algebra of rational numbers sitting there.
Yeah.
If
So
you
it's
think
kind
in
of
terms of like there
connect-
exists a unique 4th circle for every mathematical operation for rational numbers.
Exactly. Yeah. It's kind of.
I'm not sure about the division, but surely, yeah.
Apollonian gasket can be obtain the area using the self-similar ideas we used in the first
No,
lecture.
no, it's even worse. There are 3 parameters in that, right? So the
Yeah.
3 R1, R2, R3. So it is, I think, or see, I think of it in very trivialistic way. At least at a very naive, elementary way, it is hard. But people work on this and they must have results somewhere there. Yeah.
That was a simple, nice. Serpensky triangles were nice, but now it seems to be more messy and many things.
Yeah. Yeah.
So any
exactly.
like any do you know of any, like for example, fractals are found in nature, right? So like some way or other, is there anything in nature that relates to fourth circles or Apollonian gaskets, or
Uh, a faculty in our university, UREC, he thinks, or his, I think, thought is that loop quantum gravity can be described using Apollonian circles. Like he that's his aim. Like he has a feel, or his suggestion is that it can work out. So that's that should be the biggest application in it.
So now the question is, where is loop quantum gravity?
Yeah, don't ask me that. That's his thought, and I don't think that fits into this talk at all. Yeah, I don't know. Yeah, I think let me not even go there. Yeah, I mean, one of these days I can ask him to give a talk, and he can at least elaborate a little on that. But, yeah. So I think, so to answer your question, Pachi, I mean, it has applications in the sense that there are physical theories which are hard to comprehend, and there can be a connection between these structure or these geometrical structures and that, rather than asking, oh, is there a flower or is there a bacteria that has this shape? Instead, like some properties of this shape can be associated with some properties of physical theories we construct.
So loop quantum gravity has this discontinuous space, you're saying, makes use of discontinuous space. I mean, you said rational numbers. Fourth circles are rational numbers. So,
I think I shouldn't comment, right? Yeah.
Okay.
So
But
let me know.
where is discontinuity in space? Space is continuous, right?
We don't know that yet. Like somewhere it gets I mean, we talk about quantum features of space itself, right? Somewhere it's very deep level. You cannot
go beyond that? What do you call Planck's?
or you cannot penetrate, or you cannot you cannot physically enter into certain there's a limit apparently. I don't think I can. I don't use it, so I don't know. I haven't encountered it in my lives. Yeah.
Mhm. So just a side note again, away from this fourth circle, would you say that real number set is discrete and not continuous?
No, it is dense. It is dense. Even rational numbers are dense. They're not discrete. At least the way we define discreteness.
But then on the number line, we are still missing out on the irrational numbers, right?
Correct. But I think by continuous, what we mean is that give me any two rational numbers and I can find a rational number in between. and I can
No,
keep
I
going.
understand the definition of the dense. I'm just kind of visualizing it like, okay, there is a number line. These are the natural numbers or integers or rational numbers. And then
Yeah,
I ask myself that if I just stick to real numbers, then I'm missing out a whole bunch of irrational numbers on the number line.
No, real numbers is rational plus irrational.
No, not real numbers. Yeah, I think
Rational.
irrational. Yeah, rational numbers. If I stick to rational numbers, then it
Yeah,
should be considered like there should be like places on the number lines which are not mapped to anything.
True. Yes, but it's dense. It is dense, but there are missing numbers. Correct. Yeah, it is dense, but there are missing quantities in there. If you're allowed to talk about it. Like, I think if you confine yourself to rational numbers, then it is dense and continuous and you're good. But then you'll be missing numbers there. Like you can do mathematical operations on, like, for example, square root of 2 is not there in that dense structure that you build. So yeah. Yeah, so I think.
What are you doing with 4 circles, or you don't want to talk?
Oh yeah, good point. Why am I
Maybe
interested in this?
yeah, go ahead. Just
Yeah, why am I?
2 minutes, 5 minutes.
Yeah. So, so once you have a 4th circle, yeah, that's where we have a 4th circle there, right? I think we can. So I think the simple question you can ask is, if I shine light on this, there is a pattern you can form on the other side. We know how patterns are formed using circles, but how there are many circles. How does the structure lead to the pattern? What is the contribution you get? So what's the intensity of light that you will form on the other side? And I luckily could calculate that in the Rayleigh scatter. So the technical statement is that the Rayleigh scattering expression for the electromagnetic radiation or electromagnetic scattering of a 4th circle can be exactly calculated. Yeah, so that's what I did with Urek. Like Urek is the person I said who's a sort of a world expert on Apollonian gasket. So I did this calculation with him and a student. Yeah, so it's kind of a nice result. Yeah. So does that help?
Yeah.
Yeah, I think it is 1.5 hours. Yeah, Bipan? Yeah, question?
No, I'm done. I'm just saying that this is good.
Oh, it's yeah. Okay. Yes, I think it's 6 o'clock. Or in my place, it's 6 o'clock. So it's probably 4:30 in India. So I think it's 1.5 hours probably. We should try to close. What do you say?
Yeah, I'm good.
Yeah.
I'm good. Bye.
Yeah. Thanks. Yeah, thanks for all the comments and questions. Yeah. And thanks for attending. Yeah, thanks, Bipan. Thanks, Lenu Kumar. Thanks,
Shajesh.
Shruti.
Thanks,
Yeah,
Shajesh.
thanks. Yeah. Great. Hopefully it was better.
Okay.
Yeah. Okay. Bye. Okay. Bye, Lenu Kumar.